So now we are going to see the simulation of RL series circuit. So in this image or in this circuits we connected the resistance and inductance in series with each other, and this series combination is connected in series with the AC load. So these circuits will behave like a RL load, and that current waveform, current and voltage waveform. So you can see the current and voltage waveform here. This blue color shows the voltage waveform and this red color shows a current waveform. As we know that if the circuit is pure resistive, the current and voltage will be in phase with each other and there will be no phase angle difference. And when you are connecting a inductive load, the current lags the voltage by 90 degree, and when you are connecting capacitive load, pure capacitive load, the current leads the voltage by 90 degree. And here it is a combination of R and L, so there will be some phase angle difference. That means that the phase angle of these RL circuits will vary from 0 to 90 degree. The current lags the voltage, but the angle may vary from 0 to 90 degree. So that is the difference in between the other circuits. And we are going to simulate the same in the MATLAB model. Already I created a resistive circuits with the components of source, resistance, current measurement, voltage measurements and scope. I already created, and if you want to detail about these components, you can see my previous videos which is uploaded for this resistive simulation. And now you see that difference. I ran this program and now you see the difference in between the voltage and current. And here the current voltage magnitude is very low, so I am increasing that value of the resistors to 10 ohm. Okay, so here 10 ohm resistor is connected, and now you can see the phase angle difference between the voltage and current, and you see that there is no phase angle difference in between the voltage and current. So the current and voltages are in phase with each other, so there is no phase angle difference. So here the magnitude of the waveform may vary, so that depends on the load connected with the circuit. Okay, but the phase angle difference, when you are looking into the phase angle difference in between these two waveforms, there is no phase angle difference. So the phase angle difference in between these two are 0. And now I am going to change this circuits to RL by replacing the component R by RL component, and here the resistance is 10 ohm, then the inductance value is 25 millihenry is already connected. So just I am running this waveform and I show you the difference. Now you see that there is a phase angle difference in between this. So initially we can check that waveform because you see here this is the 0th instant. Here the current lags the voltage by some angle, so this is not exactly equal to 90 degree, so that depends on the value of the inductance connected with the circuit. So here you see that, so this is the 0 crossing of the current. Okay, so it is equivalent to 45 degree. Now I am changing the value of inductance from 25 millihenry to 100 millihenry. Now you can see the another phase angle difference. That's now the phase angle will increase. The phase angle between the voltage and current will increase. You see here. So now the phase angle is increased to nearly to 90 degree. It is not exactly 90 degree, but it is near to 80 degree or 90 degree. So this is the difference. Okay. So if you want to see the waveform in more clear way, you can reduce the resistance value to 5 ohm. So that will increase the current by double of the time, and now we can clearly see the waveforms. Okay. So here you see that there is no there is a phase angle difference. So when you are increasing the inductance value, you can see that when you are increasing the inductance value, so that increases the phase angle difference. And if you are decreasing that value, inductance value, that phase angle difference between the voltage will and the current will come down. Okay, so that is the theoretical versus practical concept comparison. Thank you.